Hello, my name is Gauri. Today I'm presenting my work on detecting hallucinations in large language models, those convincing but incorrect responses that can undermine trust in AI systems. This is a critical problem for any company deploying LLMs in production, from chatbots to content generation. The problem is, given a context and a claim, predict whether the claim is truthful or hallucinated. I worked with about 38,000 examples from two benchmark datasets, one being the HalloEval dataset and the other one being Truthful QA, which covers 38 categories from science to common misconceptions. This is a binary classification task where detecting hallucinations is useful in determining AI safety. Here's why this matters. A recent study found that more than 80% of users trust LLM outputs without verification. My solution helps catch those false but plausible statements before they cause harm. But the challenge is that hallucinations often sound just as confident as truthful statements. My solution uses Distilbert, a lighter and faster transformer model compared to the regular BERT, with two technical innovations. First, being class weighted loss to handle the 60-40 data imbalance, which prevented the model from just predicting hallucination for everything. And second, being the line based explainability so that users can see which words influenced each decision. This isn't just a black box, but every prediction is interpretable. The model achieved 84.5% accuracy and 86.7% F1 score on the held out dataset. I chose F1 score as my primary metric because both types of errors matters. Missing a hallucination and falsely flagging truth both carry costs. The 87% precision means that when the model flags something as hallucinated, it's right 87% of the time. And the 86% recall means that it catches 86% of actual hallucinations. The ROC area under the curve of 0.93 shows excellent discrimination across the confidence thresholds. Here's where the domain knowledge mattered. First, I implemented early stopping after discovering validation F1 peaked at epoch 4 and then declined. The model was memorizing training data and was overfitting. This saved the training time and improved final performance. Second, I chose Distilbert over BERT, not through brute force and grid search, but by analyzing the speed accuracy trade off. 60% training for less than 2% accuracy loss. For production systems, this mattered. Third, and most critically, I noticed the model initially predicted hallucinated for 99% of the cases, which is completely broken. By calculating and applying class waste balance on the 60-40 imbalance, I fixed this and achieving balanced performance. However, I didn't just trust the text metrics. I created 20 examples with simple facts. Paris is the capital of France versus Berlin is the capital of France. The model failed initially, getting only 50% right, which is equal to a random chance. Using Lime explainability, I discovered why. The model learned a spurious correlation. In the training data, truthful claims were short fragments, while hallucinations were complete sentences. So it flagged all complete sentences as hallucinations, even when true. This finding was crucial. It told me exactly when the model works and when it doesn't, which is essential for production deployment. So, what does this actually mean in practice? Right now, the system is great at helping human fact checkers by pointing out content that looks suspicious, basically large scale content moderation. But I've figured out a clear path to turning it into a fully standalone solution. Initial experiments with Wikipedia integration improved out of distribution accuracy from 50% to almost 70 to 80%. With RAGs and with RAG generation and real-time internet access, this could reach 85 to 90%, making it production ready for autonomous deployment. The second improvement that we could integrate is training on diverse QA formats to eliminate those spurious correlations that I found. There are three takeaways. First, I delivered strong performance, 86.7% F1 with full explainability through Lime, not just a black box. Second, I was able to go beyond metrics to validate meaningfulness, discovering the model's boundaries through systematic testing. I didn't just build it, I tried to understand it. Third, I identified a clear technical path to scale this from a support tool to a standalone solution with concrete evidence from Wikipedia integration experiments. As a final note, this slide shows some technical specifications I used in the project. I utilized Google Colab's collaborative environment to train and evaluate the model, which significantly reduced the time from 44 plus hours to about 10 minutes only. I also tried multiple parameters and decided on these that gave me the best performance. Thank you.